I think my pen was still playing up. We'll see how we go, but this thing seems to be broken, which is not great. I wonder if it's my screen. Let me... I wish I had some sort of cleaning material. Alright, let's fingers crossed that works and we'll see how we go. Maybe the battery wasn't dead after all. No, I should be alright. Just see how it goes. Thank you though. Alrighty, don't lose all that. Seems a little bit better. Alright, so today we've got two different problems to go through. So we're looking through plane weaves in a linear isotropic media, which I'm pretty sure Professor Hill went through today. So there's plane wave description of fields, phasor description of fields, Maxwell's equations for harmonic fields, plane wave propagation in linear isotropic media, skin depth. The other one we're looking at is parallel plate transmission line. And I believe Professor Hill is going through that a bit more later this week. Now, before we get into it too much, we'll first just go through some stuff that you might need to know from for this one. So we know that we can, we have our wave and we have this term, come on. All right, looks like I'm gonna have to use my finger in, so we'll see how this goes. We have the term e to minus j kr, right? So this is some sort of wave moving in the ART direction. But what does K represent here? So just like when we have a wave, we can represent it with the period, right? So that's the time that it takes for a single for a wave to complete a single cycle, right? In a complex domain, we can have this same thing here where it takes K, which is some sort of distance measurement, to finish one complex cycle, right? So K is representing this complex cycle. And K can be split into, it's proportional to two values, so Kr and Ki. And we'll have a look at this, but you'll see that Kr represents, so this one here, this Kr here represents the propagation, and Ki represents the decay. So if I say we have our far field, right, and it drops off 1 on R, right? We have our dipole sitting here. We got some wave like this that starts to attenuate to something smaller. This amplitude drop off is represented by this Ki, while the Kr value is in the propagating direction. And so if we're perfectly aligned, so if we got this point at the end here, oh my gosh, some point at the end, and Kr or K dot R is aligned, then we're following the point. If it's not aligned, then we're not following this point. All right. So with we can have our phasor representation of a vector field, right? So a vector field is a complex valued vector, and we can split it out. We can take our real part of this, and we split that out, so we end up with, we got our vector, we can split that out, so we've got something in the frequency domain times it by this e j omega t, right? And then we can look at, say, the electric wave. And so this spatial term, right, R, is just represented by this. And so our wave is then just split up into its frequency representation. So this term here is representing the spatial. All right, so let this K value be split into Kr and minus JKI, where Kr and Ki are real vectors. We have this here, can be represented as that, right? And so if we take the real terms of that, we end up with this equation here, right? And you can see here that we got ki, right? Negative ki. So we know that exponentials are either like that or like that, right? They're either rising or falling, and of course things are getting raised by themselves. So they're rising or falling. And so if we have this negative, it's going to be, actually I think, we're going to have some sort of attenuation, right? So that's the ki term, and then the kr term is in the direction of propagation, right? And so with real and imaginary components are collinear. Sorry, let me erase that. We get this coming out here, where k dot k, the unit vector in the direction of k is equal to 1. And so we end up with something like this, where wave is attenuated as it propagates, and is direction, k hat is direction normal to the wave front, and represents sort of the oscillations. But what do we mean by wave front? Well, say we've got our dipole here, and we've got some wave coming out. Over a long distance, eventually those waves will be so large that you'll start seeing sort of straight lines, right? The further away you get from something round, it starts to look quite flat, just like how we see the Earth as flat from our normal perspective, but we know it's round, or we think we know it's round, depending on who you believe, right? And so if we look at a surface at those points, if we take our surface at those points, these are going to be surfaces completely parallel with that wavefront, right? So this is the far plane, as we talked about last week. We have near field and far field, and the assumption is a plane at a far distance is going to be perfectly parallel with the wave at that point. So that's our wavefront. And so the amplitude and phase are the same over this plane, right? So here, 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 that's all going to be the same, right? And it's all going to be in the direction of k hat, right? And this field is represented by a B and an E. All right. So we can look at the wave propagation, right? The amplitude of the field is constant over the surface divided by k dot r. So this here and this here is going to be a constant over the surface defined. So if we look at this surface, the k dot r here and the k dot r here is going to be some constant a, and they're going to be the same. So no matter where on this plane we look, because it's all flat, because we're very far away, we're making the assumption that the amplitude is going to be the same over that surface. Surface is a plane with normal k, so k dot d, where d is the distance, the vector between the two r's, is just going to be the vector r minus r naught, which is going to be equal to 0. All right, and they're going to be a constant. Right, so a fixed distance, so we end up with that. And this is the same slide, more or less. So we can do the same thing with the surface of a constant phase is defined by this, right? So this is, sorry, before what we were looking at is this, the amplitude, right? And now we're looking at the phase, which is this term here. And for a given t, so at a specific point in time, that value there is going to be constant. And this defines a plane with a normal k, right? So same thing as before. So the planar surfaces are wave fronts. Thus, the surfaces of constant phase and constant amplitude are coplanar, uniform plane wave. And so say, like we had last week, we had some antenna out here. We can work out what the energy is of this section here. And you'll notice now that we can represent it as our xy coordinates or something to that effect. We don't have to use angular coordinates or polar coordinates. And so we can work out the energy in a given area and in turn work out the energy received at the antenna in this space. Right. And for each of these here, they'll be coplanar if the E and the H are the same. So, in example, E field polarized in the Z direction and propagation in the Y direction. So we have this. So we've got our E fields. It's polarized in the Z direction and propagating in the Y direction, right? And so we've got this Y term here, Z there. So we get this coming out of that, where that's the attenuation, right? And this is the speed, this term here. And so we might have something in the negative Y direction as well, which comes out the backwards. So the waves are attenuated as they propagate, diminish to 1 on E. Don't know how best to say that, but pretty much once they get to 1 on E of their value, it's the distance of 1 on alpha, which is the attenuation in meters, all right? And this is sort of an important term, as we'll see in a minute. So no independent sources in space and no boundaries in the space. We have some of the Maxwell's equations, right? So these shouldn't look too unfamiliar to you. And for linear isotropic medium, we have the displacement field, right, which we've seen before. We've got B, which is equal to mu H, right? So the magnetic field is equal to mu times the magnetizing field, and J is the current density. So J is equal to the conductivity of the material times the electric field, which is Ampere's law, which we've seen before, right? So these are Maxwell's equations in harmonic fields, but they don't look too unfamiliar to us, hopefully. So what we're going to do is we've got Maxwell's equations, and we've essentially got this term here, and we want to represent, or we want to get something purely in the terms of E, so we want to get rid of our B term there. And so what we're going to do is we're going to go through the steps to derive something that gives us just in terms of the electric field. So we have B here, we can substitute this into here, right? And we can then take the cross product of both sides. So we take the cross product of both sides. And the reason we're doing that is back on here we have the identity of this, right? And if we find that, we can find something related to E, hopefully, in some way, shape or form. And we can use this down here as well. So really we're looking for a way to go from H through to E, so we can use D and J down here for isotropic materials. So we take the cross product of both sides. Now the cross product, we have some identity, I believe it's given in the formula sheet, that if you take the cross product of the delta cross product of delta cross product E, you'll get this lovely equation out here. And now that's equal to this on the right hand side. And we can rearrange that right hand side slightly. So we're just going to have the del of the H field. All right, following so far? It'd be good to understand this one because you might have something similar in your exam where you've got to do a derivation. So this is where you need to understand, or at least be familiar with, the Maxwell's equations. And most of them are given in the formula sheet, but they might say you've got this, you might want to have to derive this, and you have to go through the steps to do that, right? So in isotropic material, the displacement field is equal to epsilon E, which is the electric field. And so we can rewrite that to be del dot E is equal to 1 on epsilon del dot D. And del dot D, as we saw before, is going to be the charge density, right? So this is equal to that from the last slide. So now we have this term. And because we have no free charges, as we've said on multiple occasions, if there's no free charges, then the charge density is going to be 0, right? So that effectively removes this term here, right? And so now we're left with this. Now we might have a look at the no free charges. So we'll look at the right-hand side now. So if we look at the right-hand side, we've got this crossed with H is equal to J plus, oh my God, this is so much easier with my pen. Come on, pen. No? I don't understand why this is not working. Well, I just swapped the battery. You know what, it might be the tip. I think I have a spare one in my office. I'll go change it over later. So this is equal to J plus J, which is the complex number, omega D. Oops, not B, D. We want to get rid of our magnetic field terms, and we just want to use electric field terms. So D, yes. Right, so we can replace this cross product with this, but we also know that J from Ampere's law is equal to conductivity times E. So the charge density is equal to the conductivity times the electric field, and the cross product of the H field is equal to this, which we can sub in our values now for that. Keeping in mind that D is equal to epsilon E as well. Right, and then we can take this and put it back up into here, right? Oh, sorry, not that side, my other side. Put that up into here, so we can replace that with that. And then we can take that to the other side. So the Laplacian squared of E plus that is equal to 0. Okay? So now we have this term here, and if solution is of the form phasor representation, we'll have this, right? So remember from the first slides, this can be represented by this term plus or times some complex term, right? And we use our identity here that the Laplacian squared of this is going to be equal to negative that. So if you were to rearrange this top equation here, right, we can take this, put it to this side, right? We substitute the E for this, right? So we end up with Laplacian squared E is equal to minus E naught times, it's very hard to do this without a pen, K dot R times by this term here, which I'm not going to rewrite, but times that by in there, right? So we end up with K dot K, this term here is going to be equal to this here, right? So K dot K equals this box. All right, and so what does that really mean? It means that, oh my gosh, come on. We have our dipole, we've got some wave coming off, then we might have our box, so some material that it's moving into, and it's going to attenuate very poorly because of my drawing. And that attenuation is going to be related to mu. Let's try that again. Mu, epsilon, and omega. Right? It's just the terms from in here. Sorry? So this K dot K here is equal to this, and they're both unit vectors, right? They're vectors like that, and K with itself is just going to be K squared, but it's a unit vector, so it's 1 squared, so it's just 1. So we just ignore the unit vector part. Does that make sense? So E naught is unrestricted in magnitude and also in direction. So far the solution does not need to be a transverse wave, right? Just to remind ourselves what a transverse wave is, say if we have something like this, we have a wave moving in this direction, but its amplitude, so it's rising and falling in a different plane. So transverse wave means that it's alternating in a different axis to the direction of propagation, okay? The requirement that the wave has to be transverse comes from del dot E is equal to 0. Why 0? Because there are no free charge sources, no boundaries, therefore no bound charges, right? So this E dot 0, del dot E is equal to, and if we replace it with our equation from just before, we'll get this coming out to be 0, which means that the K dot E naught term has to be 0, which means that the electric field can't be in the same direction as the propagation direction, right? Because this K here represents the direction of propagation. And so if something's dot product with itself, it's going to be 0 if it's orthogonal, right? So we have two vectors, one coming up here, which we'll call E, and one coming out here, which we'll call K. If we take the dot product of those two, because they're orthogonal to each other, remember, the dot product just means how aligned two things are. So if they're completely unaligned, then it's going to be 0. So E naught is going to be orthogonal to direction of propagation. So we've applied that now, that restriction to our field, right? And so again, you may end up having to do for your exam some sort of derivation for these things. You might have to find the impedance of the wave or something like that. And you'd have to use like the electric field divided by the magnetic field or something like that. So be prepared for some sort of derivation question, I would say. All right, so just a bit more here, but we won't go too much into that. I believe it's just the same for the magnetic field as well, right? So the magnetic field is represented by this, which I still have my razor, right? We take the dot product of those two and get 0, which means that the electric and magnetic fields have to be orthogonal to each other, which we already know, right? And if that's orthogonal to each other, then they both have to be orthogonal to the direction of propagation. All right, so wave propagation in linear isotropic media continued. So important concept, results given in formula sheet, and you can tell if something may or not be related to the exam because it'll say this is a important concept, right? So it's always a good one to look out for. So we've got this K term, and as I said before, we've got Kr and Ki, where the Ki term represents the attenuation, and the Kr term is in the direction of propagation and is related to the phase. So we can rewrite these terms and say that A is equal to Ki and B is equal to Kr, right? That alpha is the attenuation, B is the phase, and this gamma term is equal to the phase plus J B or beta. K is going to be equal to this, and we rearrange that and we can get the term in terms of gamma, all right? Again, it's just a lot of derivation math. The E field can then be represented by this, where we've replaced that term with gamma, right? And remembering that this is sort of the spatial element, right? So e to the minus gamma dot r is the spatial element. We can also define this term kappa squared, which is equal to this, and therefore we get these things out. So remember, this kappa squared here is going to be from before, is going to be this, right? So we've taken this term here, and we've got these two results. So the alpha squared is going to be this left-hand side, and beta squared is going to be the right-hand side. Example, so the E field is polarized in the Z direction and propagation in the Y direction. So we've got a similar example again. AX, AZ, beta X, and beta Z are all 0. Alpha is only in the alpha Y direction, right? So we're only moving in the Y direction. The attenuation is only going to happen into the material that we're moving into, right? And beta is equal to beta times AY. Again, it's the direction of propagation. This is our E field, right? And we times it out by these terms. Y plus direction, we've got this. Again, it's the attenuation and the speed. And then you've got the negative Y direction, all right? And again, we come to this important conclusion with 1 on E being this 1 on A meters, right? So propagation in a conductor where we've got epsilon equal to epsilon naught, mu equal to mu naught, and the conductivity, they're all real. Gamma squared is equal to this term here. And you may remember seeing this term before back in circuit theory. I'm pretty sure we've seen this when we looked at transmission line theory, and it cropped up briefly where we had this gamma term. And you'll see sort of by the end of this practical that we sort of come full circle at some point. So beta squared is equal to this and alpha squared is equal to that. The waves are attenuated as they propagate because A is non-zero, at least alpha is non-zero, right? Because we've got all real values here and all real values here. So if the frequency is 0, i.e. we're in DC, then we might see something different, but we're talking about AC, right? We're talking about alternating systems. So the alpha is going to be non-zero and the beta is going to be non-zero. If, and this is a typo on my slides, but I believe you've got the right one, this omega is much less than conductivity on permittivity. We can rearrange this to be 1 is much less than this, right? Yeah? Happy with that? Just rearranging this. This term then becomes the dominating term in these equations, right? Because this is going to be a lot bigger than this, right? So we can ignore the 1, and then this becomes essentially the square root of these terms, so we can just take out their squared, and again that's much greater than the 1, so we can just times this here by this, right? And similarly with the alpha as well. And so if we do that, you'll find that alpha and beta are similar, and at low frequencies, they're just going to be related to this, right? So the attenuation as it moves along is going to be the frequency times the material, right? And remember, this is attenuation value. You times that by the distance that it moves, right? If we go back, we're timesing that alpha value, which is a function of frequency, by the y, how far in y we've moved, right? So just keep that in mind. So it drops off like this the more as we move through y. If we then looked at the other, so again, this is an error in my slides, we got the omega is much greater than the conductivity over epsilon naught. I'm not going to write this one out because it's more complex, but you might want to do it yourself as a good example to work through. If you do that, you'll find that beta is equal to this, and interestingly enough, the attenuation is no longer a function of frequency, but is just a constant. So at those higher frequencies, right, several megahertz or gigahertz, something like that, we'll find that the attenuation is no longer a function of frequency, but just a constant value times how far along it's propagated. Right? And this leads into the skin effect. Right? So current flowing along a conductor is related to electromagnetic wave propagation in conducting medium. Consider an electric polarizing field due only to the time derivative of the vector potential difference and the negative gradient of the scalar potential difference. And we consider a conducting medium that occupies the half space y is greater than 0 and current in the z direction. So essentially we have some current moving this way, right? We're in some material. We don't really care what it is. We're in some sort of material. We have that the electric field is equal to, so we've got alternating current moving up. We have some changing electric field moving up as well in the same direction. Right? So this is going to be in the same z direction, but it's propagating in the y. So we've got something like this, right? It's moving in the y direction, but it's alternating up and down in the z direction, yeah? But what we'll find is, as we move in, it's going to attenuate, right? Does that make sense? What we've sort of what we've talked about before, right? We have our attenuation value, which is this negative alpha value. And so that's going to attenuate as it moves into the y direction, right? So that value is going to get smaller as it moves in, because this j beta term is a cosine, right? So it's just going to be the oscillations. It only goes between 0 and 1. So this e to the minus alpha y is going to be our amplitude, and that decreases as we go into y. And what this really tells us is that the current for any high frequency device is going to be sort of concentrated on the surface, right? So the current sits around here and it drops off as the further it gets in the material, which is sort of an interesting finding if you think about it. You don't sort of expect the current in a high frequency wire to be sitting on the edges. In DC it's uniform, right? The current density is spread out over the entire thing. But when we're talking about AC, high frequency, it's all on the edges of that ring as opposed to in the center or distributed or something like that. And so we have this property that we've come up multiple times, right? So it propagates and diminishes in by 1 on E in a distance of 1 on alpha, right? And we can call this skin depth, right? Where skin depth is equal is the attenuation of that field by 1 on E, which is about 37%, is going to be the skin depth, right? So where we've got a wave, right, that's going like this. Sorry, let me redraw that. So the point where this amplitude here, right, gets to about 37%, which is 1 on E, that distance that it takes to get to that point is going to be our skin depth. Does that make sense? So in a material of some sort, did I have a drawing for this? No. Let's say we got some conductor, and I think Professor Hill should have gone through this, but we'll just quickly remind ourselves. So we've got one solid cable here, right? But this distance between here and here, right, we call that the skin depth, and that's where the majority of the field and the current is going to exist. Because any further in here, it drops off more and more, right? So it's attenuating more and more. And this distance here is going to be dictated by 1 on E. So once it's attenuated to 1 on E times that maximum amplitude, that's where we call the skin depth, right? Does that make sense? Okay, so sort of a bit of a hard concept to think about, but just understand that the current sits on the edges and we define it by the term skin depth, and that skin depth is related to 1 on E times the amplitude, essentially. Right? And so we can see the effects of this at different frequencies, right? So if we're not in sort of the huge range, we're in 100 kilohertz, this term here holds, right? And so the skin depth of copper at 10 kilohertz is 0.67 millimeters, right? And for solder at 10 kilohertz, it's going to be 2 millimeters. So the majority of the current is sitting at that 2 millimeters, right? If we were into the megahertz, right? 1 megahertz is 100 times 10 kilohertz. And so we take the square root of that. So it's going to be 10 times smaller, right? Once we get up to the gigahertz, it's going to be 1,000 times smaller or something like that. And, we're down to the micrometer level or something like that. So you can imagine, we're sending signals on PCBs and stuff like that, very high frequency, high switching, and the majority of the current is sitting at the edges of those traces, right? Sort of an interesting fact more than anything. All right, let me have a drink. Is that all right? All right. So, next example, we're going to be looking at parallel plates, static magnetic field and inductance. So, previously, we've had our 2 plates, right? And if you remember a few weeks ago, we looked at the Coulomb fields on those plates, and we worked out a value of capacitance, right? In terms of physical constants. And that was equal to, I'm going to be testing my memory now, so let me just double check to make it sure I don't get it wrong. Right, we had this come out, where the capacitance was related to the material permittivity times the width divided by the height. So that was the capacitance per unit length, right? I think it was normally width times length or something like that, and then the plate separation. In this case, we're just talking about the unit length, so I'm saying 1 length, L is equal to 1 for this. I think normally we would have it as A, right, area, which is length times width. So now we're going to do the same thing, but instead of finding a value for capacitance, we want to find a value for the inductance, right? So we're looking at 2 plates. We're going to see if we can find the inductance. So consider 2 perfect conducting plates. A DC current flows in the positive Z direction in the top plate and the negative Z direction in the bottom plate. What is the magnetic flux density between the plates? And assume that the dimensions are such that A is much less than B. So the plate separation is a lot smaller than the width, right? So that only significant flux density is between the plates. So we might have, again, some sort of, so we've got our magnetic fields coming around here, but the more important part is what's happening between the plates. So we're sort of just ignoring these fringe areas again, right? Because what we're really interested in is what's happening between the 2 plates. And assume permeability of conductor and space between that of free space. So Ampere's circuital law in integral form. So over a closed loop, right? The magnetic field, it can be equivalent to the mu naught times the current, the enclosed current. So remember, before we had some sort of charge or something like that, and we drew a Gaussian around it, and we said this is the enclosed field. The same thing, we're enclosing the current. And so we've got boundary conditions, and those boundary conditions come into play again. So where we had before, we had our two plates, right? And we had like the fields going through here, right? The electric field, and we had the condition that the at the boundary point, if we had 2 different dielectrics, they had to be the same and stuff like that. So that was sort of the important point there. But this time we're looking at magnetic fields, which are going in this direction, and they'll have their own. They sort of dominate in the tangential direction as opposed to the normal to the surface, right? So this here is the normal. The electric field is in the normal to the surface. The magnetic fields are in the tangential direction, right? The tangential to that surface. And so they're going to dominate in that sort of area. So we have vector form and scalar form of this, A in the normal direction. So you can see here the difference between the 2 vectors, dot product with the normal, is going to be 0, right? So that means that the magnetic fields are tangential to the surface, right? But if we take the cross product of them, we get the current density, right? What will the magnetic flux / field density look like? So we take our 2 plates. Again, we're not really concerned with this fringe area. We're only concerned with this surface, something in here. And we look at the component normal to the plate will be 0, unless something else external causes a field. Only tangential components are what we care about. And we can use Ampere's circuital law in integral form or tangential boundary condition to find the magnitude of flux. Right? So we have this field here, B. We're looking at, again, just some wire like this, and we're going to look at each section of it. So the integral form, we split it into 4 separate sections. And again, we're sort of ignoring any of the fringes. So here, here, and here, we're going to say that the B field in those areas, for all intents and purposes, is 0. And so we only have this term here, which, if I erase my drawing, you can see it's only this here that we're concerned about, this piece here. All right? So we take the integral of that, we'll find that B, right? B is this distance of the plate, right? How wide those plates are. And the B field is going to be in the negative y direction because we've defined it to be in the negative y direction. And we're only caring about the tangential component, right? And that is equal to mu naught I enclosed. So this is the free space and enclosed current, y, because these terms are 0 essentially. And so we can have that this magnetic field B is equal to mu naught I on B in the AY direction. Now, definition of inductance. A definition of inductance is the flux divided by the current, right? So we'll have some square here, we'll have magnetic field going through here, and we times that by the current, so we get our inductance. And that is going to be equal to 1 over the current times the integral over some over some surface, right? In this case, we choose a surface which goes between the plates and cuts the magnetic field, right? The magnetic field is going in the negative y direction, right? So this is the same plate as we had before. It's going to be between the 2 plates and cuts through that, right? Remember, the flux is just the strength of the magnetic field through some area, and we're dividing that by the current traveling through these plates here, right? So the per unit length, this is a length of 1, right? So L is equal to 1. We're taking 1 unit length. We could do it here as well. Doesn't matter as long as that's a unit length of 1. Then this integral, is going to the surface is going to be this, right? In the negative AY direction, dz times dx, right? And remember, the vector for a surface is always in a normal to that plane. So if we're saying that our surface is going in the z and the x direction, then the vector for it is in the y direction. Then we have this integral here is going to be this double integral, right? So it's between 0 and a, which is our plate separation, and z to z1. So we've got 2 integrals, and as you've seen before, right? We can integrate 1 over 1 length and then over another length, right? And we get this term here, all right? So A is much less than B. We hypothesize that the structure supports a TEM propagating wave in the Z direction, not DC now. So TEM, do you know what that stands for? So it's a transverse electromagnetic wave, right? So transverse, again, just means that the oscillations happen orthogonal to the direction of propagation. So a phasor of E is given by this. Note that there are different definitions for gamma, and there may be a J in the exponential, or exponent, right? So what is this field? All right, so the field in the Z direction. Any guesses? We've got our 2 plates here, right? Separated. We have EZ. Well, if you think back to what we had before, right? When we had our electric field and we had attached our battery to it, the field is only between the 2 plates, right? It's not going to be along the plates, right? So in the Z direction, it's going to be 0. The EY is also going to be 0, right? Because it's a transverse wave. There can't be any EY component if it's transversing only in the Y direction. Magnetic field in the Z direction, this one is propagating in the Z direction. So explanation, that one the other way around, but essentially we're propagating in the Z direction. It's a transverse wave, so you can't have oscillations in the Z direction. Similarly with the H, right? The H field is also, because it's a transverse wave, it's not going to be in the Z direction. And what about in the X direction? Jenny, any idea? So the electric field and the magnetic field are orthogonal to each other, right? And they can't be in the direction of propagation, right? So can't be in the Z direction because that's the propagation. The electric field is only in the X direction, right? Because it's between the two plates. So the H field can't be in the same X direction, right? Because if it was in the same X direction, they wouldn't be orthogonal. So the HX is also going to be 0. So in this case, I believe we are propagating in the Z direction as well. Yeah. I think earlier we had an example where it was propagating in the Y direction, and I must have forgotten to mention that it was propagating in the Z direction, which might be confusing. So this one is propagating in the Z direction. So because it's a transverse electromagnetic field, we can't have it oscillating in that same direction as propagation. And then because it's between the two plates, the electric field is going to be between the two plates, and the magnetic field is going to be tangential to those plates, but not in the same direction as propagation. Yeah, so the magnetic field is in this direction, and the electric field is in that direction. Yeah, and the wave is moving in that direction. Right. Again, Professor Hill will go through a bit more this week in these lectures, but more about TM waves and guided waves. But essentially, we're talking about, so before we were talking about just waves radiating out into space, and they go in all directions. Now we're talking about guided waves, which are guided by a material, so they'll move in the direction of that material, right? So we've got some equations for this, the EZ and HZ wave propagation. We assume no free charge of the current source between the plates. Furthermore, typical conductivity of medium between plates is that. TM wave propagating in the Z direction. So as we said before, EZ and HZ are going to be 0. The TM wave, we've got our phasor representation. We can take the dot product of those, and because they are not aligned, they're going to be 0, as we suspect. Right? So our HT is equal to this, and our ET is equal to this. And remember, this is the impedance of a particular material. So for a parallel plate line above, we say that in an insulator, that the conductivity is 0, essentially. Right? If we've got an insulator, that's not going to conduct between it. What will be the electric and magnetic fields? Well, we can find the impedance using this term here, like we did last week. Right? We had a wave and a far field propagating through free space, and we had this term here. And we can replace that in the E field, right? AZ cross product with the HT, where HT is going to be represented by this in the Y direction, right? So HT, as you can see, is a function of Z, right? Because that field attenuates as it moves through the material. So its amplitude is going to reduce or change with the Z direction movement, but its vector is in the direction of Y, right? And is also a function of frequency. We have A cross product with that, or AZ cross product with that, which is fine. We'll just end up in the AX direction, right? And so for the guided waves, we end up with this, where we've got electric fields up and down, and magnetic fields are in and out of the page, right? So we've got crosses and dots in and out of the page for the magnetic field, and we see that our current densities are increasing and decreasing in certain areas. And our charge density is changing as well along those plates for our guided wave. Alrighty, so from before, this is a good example to work through. Previously, we've calculated what C might be for a two-plate system. We've now worked out what the inductance is, right? That was the last example. And we can use that to work out what the characteristic impedance of this two-plate system is, right? It's going to be the square root of L on C, which is what this ends up being, right? So this is sort of a good example to go through, and I think Professor Hill will do another example in class, but if you remember from your transmission line sort of investigation, you might have found that the characteristic impedance was related to this. So we've just sort of come full circle back to transmission lines and how we get the conductance, the capacitance and inductance of that transmission line, right? Because we're assuming the transmission line is really long compared to our system. We can do these equations, and you can do it for our coaxial cable, which I think Professor Hill will do in class. And hopefully that'll give you a better idea of these TM guided waves. All right, and so that's it for today. Now, in terms of what I would recommend you might want to look through for the exam, go back through these two examples that we've just done today. Then also have a look at maybe the capacitor ones again, because we've done multiple examples of those. And then if you remember something like the rings, how we had one inducing a field, how we had an alternating current moving through a ring, created a magnetic field which induced created an electric field that induced a current in the other ring, something like that. So we had that a few weeks ago, so have a look through those practical examples. And then Professor Hill will give some more tips as well. And that's it. Good luck.